W1 VLF.
Hey everybody, welcome back. My name is Paul, W1 VLF, and we're in the lab. This is a follow-up to my common mode choke video that I did a few days ago. And the reason I'm doing this is I got so many questions about how many turns do I need, what kind of coax, how did you choose those cores, why are there 6 of them, just lots of questions, and I think it would be easier to make one that's reproducible by anyone. To be honest, those cores were something that I scavenged out of old power supplies. I checked them with my LCR meter and they made very good inductance per turn, so I used those, and I guess I kind of lucked out. They are the common mode choke appears to work fairly well up to about a couple of megahertz, and for the kind of work I do, I don't really, I'm not too worried about that. A couple of things though. So we're going to build it out of components that everybody can get. But before we talk about that, I just want to say one thing. You need 3 things in your shop. WD-40, or the European equivalent if this is not available. This is for things that are supposed to move but don't. A couple of shots of this will get them moving. If you have something that's moving around and it shouldn't be, duct tape. Best stuff on earth. And man's second best friend, PVC pipe. And the reason why I'm looking at this PVC pipe is because this is going to be the container. There are so many different elbows and end cap configurations, diameters. This particular diameter is what? This is 1.5 inches. And the reason why I chose 1.5 inches is because the 1-inch cores that we're going to be using fit nice and snugly in the end here. And you'll see. I'm going to back away from the Group W bench here and then zoom in on the components we'll be using. But so let's take a look at that, and I'll be right back. Okay, we're back at the Group W bench. In this case, I have RG178. It's 50 ohm coax. I happen to have it around, I think it's about 1/10 of an inch in diameter. And for a pair of cores, these are number 75s, 1 inch, and I'll show you where to get these. Aero Electronics is where I got mine. In a reasonable quantity, they're $1.36 a piece. So PVC pipe, right? Caps, small section in the middle. By the way, always chamfer the outside and inside ends when you're working with PVC. When you cut it with a hacksaw, I did this in a lathe because I have a lathe. So the inside's chamfered and so is the outside, because it can end up being pretty sharp. An end cap. So it's kind of, this is what it's going to look like, basically. And if you watertight where the BNC goes through each end, you should be able to put this outside without any problem. So let me see. Let me grab the tape measure. Okay, so that's about 3.5 inches worth of PVC. A couple of caps, 1 on each end. Some BNC connectors. These are nothing special. And the cores. And I am using 10 feet of RG178. The 178 is small enough so that I can get 25 turns through my stack of cores. And then the cores will still fit nicely inside this 1.5 inches. So let me show you how I get these cores glued together so that they're one continuous piece. That's the other question that came up. There's a gentleman, Everett, who's been posting quite a bit of really good information about using different core materials. These cores, if you look them up, you'll find out that they become kind of ineffective up around 15 megahertz. So again, this is more designed for VLF, LF, and medium wave frequencies. you're going to use another material if you're going to go to higher frequencies than that. So let me set up for the next shot and I will be back. Okay, well, I can't really tell how well the video is going to look here, but hopefully you'll get the general idea. I use a piece of angle bracket here. This happens to be aluminum. I think it's 2 inches by 2 inches. And it helps line these up when you're going to glue them together. Just the way that they're natural. These things are designed pretty high tolerances, and everything fits really snugly. So let me just glue one of these babies up. And you know, once you open one of these things, you may as well throw it away, because 20 minutes later it's not going to be useful anymore. So I'm going to just put a good coating all around the perimeter. Okay. Trying not to get any on your fingers. I'm going to line up my 275s again. Let me get rid of that. Look at that, I got some on my finger. Okay, there's my 75, my 75. Oop, guess you should tighten that up a little bit, huh? Alright, so you see what really happens? Alright, so needless to say, alright, I'm gonna just hold these together until they're, take my word for it, once you get these together, they're not going to come apart if you put the right amount of glue in there. Okay, so that's pretty good. I'm going to clean these up and I'll be back. Okay, here's our two number 75 cores connected together. They're not going anywhere. And 10 feet of RG178. There's a little black piece of tape here. That tells me where the halfway point is. I think 10 feet is a little bit more than I needed. I really need about 9 feet. I calculated with a regular piece of wire how to get 25 turns on one of these cores and doubled it. So start by just winding. Where's my mark? Getting up to the first mark, the middle. And then we're going to wind. At least this way you don't have to thread through 10 feet. You only need to thread through 5 feet. So I'm going to wind this because it's not very exciting, and I'll show you what happens, what it looks like when I'm done. Okay, we're back at the Group W bench, and I managed to get 30 turns on these two cores. Now if you were to put a third or fourth core, you'd get even more inductance, but 30 turns is what I ended up getting with the RG178. And watch how nicely this fits into the PVC pipe here. Okay, just slides wonderfully right in there. Leaves about, oh, I don't know, an inch and a half or so on either side. So now we'll be able to take our connection, we'll cut it off somewhere around here, solder it up to this PVC pipe with the BNC in it. You really probably can't see that, but there's a ground and also the center conductor in there. And you can do that out here. So you'll be able to solder away and then just push the excess in. If you really wanted to, you could put a little bit of hot glue in here to keep the core, or maybe some foam rubber to try and keep the core centered in there, but it's not necessary. And again, it slips in very nicely. And there's maybe about a 1/4 inch of play on either side. So let's take a look at this on the LCR meter, and let's look at it on the network analyzer and see what happens because of the inductance in the original versus the inductance here. So let's take a look at that. Let me set up. Alright, so we're back with our trusty old impedance meter. I think this is ESI. Somewhere around here it says what it is. 253. We're in the inductance mode. So let's take a look and see what the... And remember, I'm going to the shield here, or to the outside of the BNC connectors. Alright, so this one, the original one, has about 66 millihenries of inductance. Okay, we'll get that out of here. That doesn't tell the whole story, but it was a pretty good indicator of what was gonna happen. Now I've just stripped back these cables on the one we just made, and we're at, because we only have 30 turns, this thing probably has over 100 turns, and it has 6 cores instead of 2. So here we're at sitting at around 16 millihenries. But that, again, that doesn't tell the whole story. I'm going to set up now on the network analyzer and show you how these two perform as far as common mode chokes. Well, actually, before I do that, right, got the end cap itself, the end cap with a hole in it, the end cap with the BNC in it. So I'm going to solder these up, and then we'll take a look at it. Okay? And let me show you one other thing too. Let me move this stuff out of the way. Here's a little test fixture that I made. I guess something like that. And it's BNC, BNC. They're both soldered to this ground plane. And then there's a clip in the middle. Okay, and here's ground. So if you want to test with this, this is just for calibrating it. If you want to test a choke like this, you simply put the shield here and the shield here, and then look at what you have on the network analyzer. And I'll do the same thing with this one. But if you were testing a transformer, for instance, I think I have one over here somewhere. Okay, no I don't. But here's a kind of an experimental one I made. You would go between the ground connection here. This would be the input of the transformer, and the output would go here. And then you'd be able to see. And I know what you're saying. Look at all those wires hanging all over the place. Well, the truth is, in the LF and longwaves and VLF bands, and even up into medium frequencies, what we're looking at here is not going to make a bit of difference. If you were doing scientific measurements, you would be, oh my God, we better shorten these up and get a super impedance matched setup to do this with. But the reality is, you can do this with on those frequencies and not have to really worry. Okay. So the network analyzer would connect to this piece here, BNC in and out. The tracking generator would go on, say, this side, and the spectrum analyzer on this side. So that's enough of that. So I'm going to go, we'll shut that off, and we'll go take a picture of this, and then I'll do a voiceover. Alright, as to what's going on. So one more time, very nice fit. You can put black tape around this to snug these up and make it even a better fit, so that it won't move around in there, or put foam or hot glue, whatever you want. Again, not critical. I'll be back. Okay. Unfortunately, I have to do this by shooting the camera at it. I'm right here, but I'll be running the mouse. Hopefully you can see this. Left-hand side of the sweep starts at 10 kilohertz. The right-hand side of the sweep ends at 3 megahertz. In this particular case, I'm not all that concerned about noises above 3 megahertz. In fact, there don't really seem to be that much. There really doesn't seem to be that much noise. So my concern has always been below 3 megahertz. So the first thing we're going to do is we're going to put on the test jig the original sweep. Excuse me, the original common mode choke. And I'm going to stop this. I'm going to do a max hold, and I'm going to stop it from updating. So now we can see that down here, I'll put a marker in. I'll grab some of these and put them in, high resolution videos, because I can save all these, so or in snapshots. And that's the other thing. At the end, I'm going to have close-ups of all the different pieces that I'm working with here. So if you want to stick around to the end and see close-ups of, like, all the stuff, you know what I mean. All right. So marker 1 is at 60 kilohertz, and there's a huge amount of attenuation there. According to this, in a 50 ohm system, there is 55 dB of attenuation. Now it rises as we go up in frequency. At 3 megahertz, it's only about 15 dB, and I think a lot of that has to do with the multiple amount of windings that you have on this one, the inner lead capacitance. So here, although we have on this core, although we only have 30 windings, let's see what the frequency response looks like. I'm going to put on number 2, trace number 2, and there it is down at the bottom because I don't have anything connected. And now we're going to connect it to our test jig and see what this looks like. Okay, now I'll store both of them. Over here, max hold, and then we don't want to update anymore. Okay, so 2 cores, 2 of the number 75 cores. Wow, you got to remind me to put up the slate, tells you where to get them. But it's Aero Electronics. I will give you the model number. If I don't, somebody yell at me in the comments. So let's look at 3 megahertz. 3 megahertz, the original choke has, again in a 50 ohm system, about 15 dB of attenuation. Here, in this one, with the minimal amount of turns, very little inner electrode or inner turn capacitance, we end up with, let's see, about 40 dB of attenuation. And it stays that way, gets better. We're now at 1.3 megahertz. We're better than 40. We're at 45. And the real dip here is at 400 400 kilohertz. And the crossover point is right here at 100 kilohertz. So the original common mode choke has an advantage here, but nowhere else. I'll do these in a JPEG, because I can save these off, and then you'll be able to pause it and really get a good clear look at what's going on. So again, up here the marker's at 3 megahertz. We're down 15 dB here. Actually, let me put a couple of markers on. We'll put on marker number 2, and we'll put it on trace 2. Okay, so the difference is between 15 and 36 dB, the red being the new choke that we just made. So let's go right about here. There's marker 1. Let's go back to marker 1 and move that to the same place. So at 1.8 megahertz, you have a difference of, with the original choke, of 18 dB. Now it's down to 40. Okay, let's go down to, what's this, 610 kilohertz. You're at 28 dB of loss through that choke on the original one. And let's go number 2, do the same thing, and we're at 52 dB, 53 dB of loss. Where they really, where the original cores seem to take over is right here at about 160 kilohertz and below. And it's not that much of an advantage. So choosing the right core is really important. And again, pop this off. That's this little guy right here. All right. So I'm going to save some of these pictures and I'll be back. All right, so some final thoughts about the two common mode chokes. The original with the unobtainium ferrite cores, 1, 2, 3, 6 of them in it, or the latest version with the two, you can get them for $1.36 a piece cores, and a couple of BNCs. A word of caution. Make sure that you're really comfortable with the fact that you've got this soldered in place, because once you put the PVC cement on here, it's never coming apart again. I guess that's it. Oh, I'm going to have to break this up into two pieces because it's already kind of long. The actual on-air test between this and this, that's going to take me a little time to figure out how to exactly do that, because I'm not just shorting out the choke itself. I'm going to have to be switching between the two, so that's going to have to be another video. But I guarantee you this one here is every bit as good, and except for at the very lowest of frequencies, below 60 kilohertz. And I don't see a lot of, from my experience, I don't see a lot of noise there. But this one's far superior all the way up to 2 megahertz, and I would assume above that as well. Lower insertion loss, takes about an hour to make. Greater attenuation. To me, I don't think there's any choice. But the proof of the pudding will be when I try them. But in my experience, this is going to be the better device. So thanks a lot for joining me. Stay tuned till the end of the video. I'll have a whole bunch of shots, close-ups of these, and I'm even going to try a little experiment with some free music at the end, so you won't fall asleep while you're looking at the close-up detail shots. And the next part 2 of this video will be the performance in the system. All right, any questions, let me know. Please subscribe. A ton of people have subscribed. Thank you very much, because you know this takes a lot of work. Doesn't seem like it, right? I know I've watched videos for years thinking, wow, that's not that hard. And then when you try to do it, it's another whole story. Thanks a lot again. This is W1 VLF 73, and I'm good in the call book. So here's the link to Aero Electronics, and you can see the part number there, as well as the $1.36 per core. Very inexpensive, a great deal, and if you order for over $50 from them, you get free shipping. I have no affiliation with them. It's just that they had the best price for the core, and that's where I bought them. So here's the graph showing the two common mode chokes. If you look at the blue and red, you can see that the attenuation at 3 megahertz in the red is significantly greater, and it stays that way until 160 kilohertz. And below that, you still have quite a bit of attenuation until you get down to the very low frequencies, down around 60 kilohertz. But my money is on the new red graph here with the dual cores. I'm looking forward to trying that out in my system. One final slide here, and this is the insertion loss between the two different cores. This is how much signal is lost passing through the cores, not the attenuation in the shield, which would be in series with any noises leaving your home. You can see that I had to go to 2 dB per division just to see how much loss there is. And look at the two markers there. There's less than a half a dB loss through the cores, so totally insignificant.